Alright, so let's get started for day number 2. I hope you had a good sleep last night. So today, in day number 2, we're going to discuss how do we measure photons. Measuring photons really means measuring the quantum state of photons. And this has a special name, it's called quantum state tomography. So you get a basic idea of quantum state tomography, how state tomography is done. The second thing that we're going to look at is two examples of algorithms. One is the Deutsch-Dosa algorithm, the second is the Grover search algorithm. And why do I choose the Grover search algorithm? Because tomorrow, through an example based on measurement-based quantum computing with photons, I'll see how the Grover search algorithm is implemented on a real system. The third thing I'll do is talk a little bit about mathematically quantum erasure. In the second half of the day, after a brief break, I'm going to show you some experimental results on my own slides of how single photons can be generated, how they can be manipulated, processed, and measured, and through a variety of experiments, how key concepts in quantum information and quantum computing can be demonstrated in a laboratory. So this is the plan for today. Tomorrow we're going to look at measurement-based quantum computing. We'll start off with teleportation, 1 qubit teleportation, 1 bit teleportation, followed by cluster states. And how do we implement 1 and 2 qubit operations with cluster states? So this is the plan for today and tomorrow. So before I begin this session, are there any outstanding questions? All right, so I think so far so good. So let's see how do we measure photons or the quantum. Measuring photons really means measuring the quantum state of photons. Process for quantum state tomography. Now, all right. So generally, we know that the quantum state can be represented with a ket. Okay, but this is partially true. It's not always true. Only certain kinds of states can be represented by kets, and these are pure quantum states. Pure quantum states live on the surface of this block sphere. If you're talking about single qubits, of course, you also have multi-qubit state, but the generalization of a quantum state is the concept of the density operator. The density operator rho is an operator which is also representative of quantum state, and it's more general than a pure quantum state representation because it's very hard to prepare pure quantum states. It's really, really hard. For photons, it's relatively easier, but still, it's impossible to create a perfect quantum state. So even if you were to prepare a quantum state, which is pure, with time it decoheres, it kind of loses its coherence. So a general description of a quantum state is through density operator. And if I were, even a pure quantum state can be represented by density operator. So how do I define the density operator? If I were to take the quantum state psi, the ket, and I juxtapose this with the bra, the corresponding bra, I form what is called an outer product. So this was an example of an inner product bracket which produces scalar which represented the overlap between two vectors. However, if the ket is followed by a bra, this is called an outer product. And if the ket is followed by the bra itself, it represents a density operator. Now let's look at an example. Suppose, first of all, let's see what this physically means. Suppose I have a pure quantum state, AB, A and B are complex numbers. The corresponding bra would be the row vector A star B star. And if I were to compose the two together in the form of an outer product, I would get bra A B divided by A star B star. Now I can form the matrix product. I will get A mod square, A B star, A star B, and B mod square. So this is an example of a density operator. Now, if you notice the trace of this density operator, which is the sum of diagonal elements of all is equal to 1. And if I were to take the eigenvalues of the density operator, they will always be positive or 0 at least. So this operator rho has three properties. It's Hermitian, which means the diagonal of the operator is equal to the operator itself. Its trace is 1, and it's semi-definite positive, which means its eigenvalues cannot be negative. So this is a property of density operator, but this is for a pure quantum state. A pure quantum state can be represented either by a ket, a vector, or a density operator. However, general states are not pure. So if I were to take pure quantum states, say some states in the state get 0, some states in the state get 1, and then I would put them together in a box and jumble them up. So what's the quantum state for the entire box? Or if I were to choose one, so if I have suppose hypothetical kind of example, if I were to choose put particles in this box in the state get 0, and then I would put some particles in the box state get 1, and then I jumble them up and I open the box and I randomly pick up one particle from this. So what would be the quantum state of this particle? It's if you're talking about quantum statistical mechanics, the quantum state of this one particle is going to be an incoherent picture of the two kinds of states. And it's not a coherent superposition, it's not a superposition. So this state will not be at 0 plus 1 over 2. This is incorrect. This is not the quantum state because we don't have a pure quantum state any longer. The best description for the quantum state of one particle that is randomly extracted from this jumbled up box is through density operator rho. And that density operator is an incoherent mixture, a statistical mixture of two quantum states, one corresponding to get 0 and one corresponding to get 1. I also need to normalize, so I divide all of this by 2. So this is a density operator. This is an example of a density operator, totally random density operator. So in general, a density operator is a random mixture, an incoherent mixture of pure quantum states. So if I were to take the quantum states, say psi k, and form the outer product of psi k with itself, and take some amount of this psi k, psi k is now a real number, and I form this convex sum over all k's. This is the general definition of a density operator. Okay. So density operators can define pure as well as not pure quantum states. Not pure quantum states are called mixed quantum states. So, for example, I could have 1/3 of get H bra H plus 2/3 of get B bra B. This is a legitimate density operator. And so on. I can have 1/6 of superposition state H and 5 by 6 of H plus V under 2 with its graph H plus V under 2. So I can combine pure quantum states together and even combine mixed quantum states together to form an overall density operator. And the good thing is that each particle, each photon that you look at, so forming a density operator does not mean that it's valid for an ensemble of photons or a large number of photons. Even if you were to take one photon out of it, its description would be through density operator. The density operator does not necessarily refer to a large ensemble or large countable ensemble of particles of photons. Even a single photon will have a description that is best explicable by a density operator. Okay. So, if I were to take kind of what's the most random mixture that you can make? So, if you're talking about a photon polarization, what's the most random mixture that you can make? You can take photon is to be either in the horizontal or vertically polarized state. So the most random thing that you can make is ket H bra H plus ket V bra V over root 2. And if I form the operator for this in matrix form, sorry. So if I form the matrix for this is half 0 0 half. Okay. This is called a maximally mixed state. Maximally mixed. Maximally mixed. And you can define the degree of mixedness or purity through the operator trace of rho square. You take the square of the density operator, find its trace. This is less than or equal to 1. And it's greater than or equal to, the base of rho square. If this equals 1, this is an example of a pure quantum state. Okay? Because rho is a projective operator. Rho square for pure quantum state is like this. Okay, since this middle thing is identity, you have to. Okay. And for maximally mixed state, this is 1 over the dimensionality of the system. If you're talking about qubits, 1 over qubits per n, and so on. All right, so now let's move on to entangled states. And let's try to kind of get some idea of the density operator for entangled states. Remember that what I'm trying to do is what are we going to measure? We're going to measure the density operator of photons. That's when first of all describe what the density operator is. So now if I have a Bell quantum state, which is maximally mixed, so it's suppose the state is pure, and it's this state 0 0 plus 1 1. It's an entangled state. The density operator for this state will of course be given by this form. Okay. And if I were to write down this in matrix notation, this is what it's going to look like. Now, quantum state tomography really means that I want to find out in general rho. So in general, rho will have, if you're talking about a 2 qubit state, 2 photons, the polarization of 2 photons, it's going to be a 4 by 4 matrix, whose trace is going to be 1 remission, positive eigenvalues or non-negative eigenvalues, semi-definite positive, and it will have these 16 elements. Okay, so it will have these 16 elements, but Not all of these elements are independent because the trace has to be one. So there are 15 independent elements. In fact, hermeticity imposes additional constraints. So the upper, if you just have the upper triangular part of the density matrix, you can figure out what the lower triangular part is because of hermeticity. This term is going to be the complex conjugate of this term is going to be the complex conjugate of this term, this of this, and so on, because the matrix has to be Hermitian. Now, quantum state homography really means that you want to find out all of these 16 elements through a series of experiments. So you have photons coming in, and you want to do tomography on the photons so that you can measure what the quantum state is. Remember that when you do quantum information processing, there are certain criteria that you need to follow, which I call the intrinsic criteria. First of all, you need to initialize your quantum states, you need to do quantum state transformations in a mitigating decoherence. Your system needs to be scalable, you need to measure your quantum states and so on. So there are certain criteria. So right now I'm talking about measuring the quantum state or doing quantum state tomography. So this is what the density operator of an entangled state looks like. Now, the point is, if I have a totally random state, suppose I'm talking about two photons, a 2-qubit length, the totally random state is identity normalized because the case has to be one. It's just an identity matrix. This is maximally mixed for 2 qubits. Now suppose I have, is the state entangled? Question. Can a maximally mixed state be entangled? No, it cannot be entangled. But remember one important thing. There is what is called an ensemble fallacy. An ensemble fallacy really means it's a philosophical argument that if you have a kind of random state, totally random state, maximally mixed, it can be decomposed in an infinite variety of ways. For example, it can be decomposed as 1 by 4 HH plus HV plus VH plus FBV. Or you can also decomposes as sum of all 4 orthogonal Dell states, the singlets and the triplets. So the decomposition is one matter, but the state overall remains separable. It's not rectangular, a maximally mixed state, it's not integral. So what about the state of this kind? If I have a density operator, this I know is an entangled state, correct? This is entangled because it's a pure get 5 plus is a pure Bell state, and a pure Bell state is entangled, and this is just a density operator for a pure Bell state. Now suppose I mix a Bell state with a maximally mixed state. Okay, so I have some photons, pair of photons, and the Bell state decoheres, and the Bell state tries to move to the maximally mixed state. Decoherence is trying to remove the entanglement. So at some point in time, in an experiment, I have a Bell state, and it's intermixed with some maximally mixed state, which means I take the sum of these states. But how much? I need, say, epsilon of this, and I have 1 minus epsilon of this. So now I need these factors because I want to keep the overall density operator trace 1. So I take a fraction of the Bell state, epsilon, and a fraction of the maximally mixed state, 1 minus epsilon, and epsilon is some factor between 0 and 1. So now I have, is my state entangled or not? Question. So I give you 1 minute to think about the question. 1 minute. Okay, just think about it. My question is this overall state entangled? I know that this alone is entangled, this alone is separable, Now I mix the two. The state has decoded into this state. Is this state entangled? No. Can it ever be entangled? So this is the state. Okay. Can it ever be entangled? Are there some conditions when this can be entangled? Can anyone who's worked with this, can anyone kind of interject and answer this? Yeah. Less probability. Okay, so it all depends upon how much is epsilon. So intuitively, if epsilon is large, then there is the idea, the concept, there is more entanglement in it. If epsilon is small, there is less entanglement. In fact, there are bounds. There is a threshold for epsilon. Epsilon is beyond a certain value, the state will be entangled, and less than a certain value, the state will be non-entangled, separate. So whenever you have a density operator, you need to do some kind of test. Your litmus test to check whether the state is entangled or not, whether that density operator gives you an entangled state or not, whether entanglement survives the attacks of equivalence, whether the entanglement is robust. This is very important for cluster state quantum computing, by the way. So just to give you an example of a test, what we could do is there are different kinds of tests that can be performed. And these tests are easier for 2 qubits, for a qubit and a qubit, 2 level and the 3 level quantum system, for 3 qubits, for a qubit and a system which has 2 is for p levels, where p is a prime number. But it's very difficult to come up with generalized tests for multi-qubit states that can check whether the state is entangled or not. But for 2 qubits, it's easy and it's well known. So one test that I would like to mention here to verify entanglement is if I were to form a matrix for this, let's try to kind of do one small calculation. 1 minus epsilon over 4, 1, 1, 1, 1, all zeros. This is the first part. This one. Okay. And now I can write down this thing plus epsilon of 1, 1, 0, 0, 0, 0, 0, 0, 0. Now I form this sum over here. And I just have done this calculation for you already, I think. So it's 1 plus epsilon over 4, 0, 0, epsilon 2, 0, 1 minus epsilon over 4, 0, 0, 0, 0, 1 minus epsilon over 4, 0, epsilon 2, 0, 0, plus. Okay. So this is the density operator. Okay, for this state rho. Or by the way, this such a state is called a Werner state. Werner state. Werner. Now, this is legitimate density operator because the trace is 1, its dimension, and so on. Now, the test that can be done, the one kind of test is you take a partial transpose. What the partial transpose does is that you just transpose one of the photons, the state of one of the photons. So if I'm going to transpose, so let me define the partial transpose. If rho is my density operator, the transpose of rho with respect to A is such that if I take the elements of this, the first qubit has been swapped. So This is the original density operator in which I and K have been swapped. This is how I define the partial transpose with respect to the first qubit. Now, if I were to perform this operation on my density operator, this density operator, what I'm really going to do is I can divide this matrix into 4 submatrices. And I swap this submatrix with this submatrix. This is the partial transpose with respect to the first qubit. I can also do the partial transpose with respect to the second qubit. If I were to do that, I will just take individually the transpose of this, the transpose of this, transpose of this submatrix, and so on. But I am doing the transpose with respect to the first qubit over here. So now I do this transpose. So when I do this transpose, my new matrix partial transpose A becomes. So let me kind of keep that original matrix in view as well. So you can't seem to come. This is my matrix, original. I just transpose, and please write down the result. I'm unable to zoom in too much. So I get 1 plus epsilon equal 4, 0, 0, 1 minus epsilon over 4, 0, 0, epsilon over 2, 0, 0, epsilon over 2, 1 minus epsilon over 4, 0, 0, 0, 1 plus epsilon over 4. This is my partially transposed matrix from the original. So you just compare, look at the original. I just take this block and put it here, and this block I put it here. So this epsilon over 2 comes here, this epsilon over 2 comes here. So there were zeros in this position, now we have epsilon over 2 over here. The other terms remain the same. Right, so this is my density operator. Transposed. Now, if the original density operator were entangled or separable, if the original density matrix were separable, then doing the transpose of one of the density operators does not make any difference. The eigenvalues of the overall partial transpose matrix will still remain non-negative. However, if a negative eigenvalue appears in this after partial transposition, it means that originally the density operator cannot be written as a direct product of two density operators. So you do a partial transpose and then find the eigenvalues of this. Now, what are the eigenvalues of this operator? Two of them are very clear. This is one eigenvalue. Is this always positive? Always positive. So epsilon is between 0 and 1. This is also always positive. So you just have to focus on this submatrix and find the eigenvalues here of this subblock. Let's see what the eigenvalues of this submatrix look like. Now, if I were to, so just focus on these. So the eigenvalues are, there are 4 eigenvalues, of course. 1 plus epsilon over 4 is one of them. The other, this one, and 2 more. Now you can do kind of simple school algebra to find the eigenvalues of this block. I know that this is unit operator with 1 in the diagonal. This is like a polymatrix X. The polymatrix has 2 eigenvalues. One is positive, 1, the other is -1. So it's easy, I can do by inspection, the eigenvalues, one of them is going to be 1 plus 1 minus epsilon over 4 plus epsilon over 2, and the other is 1 minus epsilon over 4 minus epsilon over 2. So the eigenvalues of rho are transposed are 1 plus epsilon over 4, 1 plus epsilon over 4, which is always positive. This thing is, again, I think 1 plus epsilon over 4, whereas this object here, this object, is 1 minus 3 epsilon over 4. Correct? So these are the 4 eigenvalues of the partially transposed matrix. Now, the first three will always be positive, but this has a potential to become negative, and that happens when epsilon is less than 1 over 3. So whenever epsilon is greater than 1 over 3, sorry, whenever epsilon is greater than 1 over 3, this term becomes negative. So between 33% and 100%, if that's the value of epsilon, the state will be entangled, otherwise it will be separable. So you have a density operator of an entangled state, and it's mixing with the maximally weak state. You need to perform some kind of mathematical test to check whether it's entangled or not. Okay, so we can form a region. If this is epsilon, this is 1, this is 0, this is 1 by 3. Here you have entangled states, and here you have separable states. Okay. So the density operator for an entangled state needs to be verified closely. There are other tests. One of the important tests is concurrence test. You find out the eigenvalues of some other operator derived from the density operator and see if the eigenvalues turn out to be negative or not. So there are other kind of tests that can perform to verify for entanglement. Now, why are the Bell states? Any questions up to this point before we move on to state homology?
I have a question. Is there any degree of entanglement? I mean, can you just say entanglement or not, or is it?
So this is binary test, whether there is entanglement or not. For the degree of entanglement, you need the concurrence. One simple thing to look at for 2 qubits is the concurrence. The concurrence can also be derived from the density operator. That is the degree of entanglement. It's a monotonic function of the degree of entanglement. Monotonic means higher the value of the concurrence, higher the degree of entanglement. So this is only a binary test. It's called the positivity of the partial transpose test, PPT test, or the Rorschach test, Now, why is the Bell state maximally entangled? Why is it called maximally entangled? So this comes to the question where Professor is asking. What do you mean by maximally entangled? The degree of entanglement in the Bell state for 2 qubits is maximum. You cannot have more entanglement than that. How can you verify this? What does that mean? Yes? What do you mean?
So when you measure it for some time, you're going to find it HH or BB. There's no other option.
So it's 50-50. So 50-50 is maximal for 2%. Yes, you're absolutely right. Absolutely right. The best way to look at this, however, is to the reduced density operator. Now, what is the reduced density operator of a maximally entangled state? 50-50 means maximally random. You just look at one qubit, it's maximally random. Right? That's what I think you're trying to say. So if you just look at one qubit in an entangled state, suppose you generate 2 photons. So there's some process, I'll show you in the later half today. There is a pump beam coming in, and there is a crystal, a down conversion crystal, and two photons come out. And they're entangled. So the state that we produce over here is, let's suppose it's maximally entangled, the bell state. Now if I want to place detectors, so I place the polarizing beam splitter here, and I place the polarizing beam splitter here, get zero channel, so get H channel, get V channel, H channel, V channel, and I place these detectors over here. That's what we get D1, D2, D3, D4. Now whenever D1 hits, D3 will also hit. Whenever D2 hits, D4 will hit. If there are no experimental imperfections. So there is a perfect correlation. However, if I throw this qubit into a dustbin, I don't see it, I don't observe it, I don't care about it. We just look at one of the photons. This photon on itself is going to appear like a maximally mixed state. Because there's 50% probability that D1 takes and 50% probability that D2 takes. Since it's maximally mixed, since these probabilities are half and half, if I don't care about the other photon, if that information is useless to me, I just throw it out in the dustbin, I don't care about it. Then this is photon to one of the parties is completely random. It's maximally mixed. So if you just look at the density operator for one subsystem out of the composite system, it's going to be totally random. Now this system is called maximally entangled because the reduced density operator of either of the photons is maximally fixed. So in order to, this is a very useful concept, and I think in cluster state computing we should really know about this, is the idea of the reduced density operator. So the reduced density operator, I have a two qubit system A cross B. A is the state of the first qubit and B is the Hilbert space of the second qubit. The reduced density operator of A is formed by taking rho, the combined density operator, and tracing out the second qubit. Trace out the second qubit. Trace out the second qubit means washing away, averaging out its effect. This is called, this operation trace with respect to B. It's called a partial trace. So I take the composite density operator for the combined system and I trace out one qubit. What remains is the other qubit, A. Okay, so this process can be defined. Remember, I can write down the mathematical definition of this reduced density operator. Remember, whenever I write density operator, it has terms in it. Say for two qubits, I, J, K, L. So I, J is here, K, L represents the column. So with I, J, K, L, each one of them could be 0, 1. So you know quantum mechanics already. So an element of the density operator, I, J, K, Lth element, is given by this for rho I instead with J, K tensor with L. This is one element of the density operator. One element of the density operator. So likewise, if I vary I and J 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, I get all the 16 elements in the density operator. For example, For example, so I have that, I know that some, I can see faces and some faces need more explanation. So suppose I have these 16 elements. I choose one element, say I choose this element. I'm just describing the notation here. So this element row is, the subscript will be, this is, if I look at the rows, it's 0, 0, 0, 1, 1, 0. 1, 0 row, column is also 0, 0, 0, 1, 1, 0. This is how I'm identifying the elements. Or this is equal to the density operator. Okay, 1, bra 1, okay, bra 0, F 1, F 0, okay. So this element and this position is being identified by these indices 1, 0, 0. And these are the bras and the caps, okay? So this is my notation here. So if I were to find out the reduced density operator of A, now I'm getting a 2 by 2 density operator because I just have one qubit. Initially I had 2 qubits, so I had a 4 by 4 matrix. Now the reduced density operator is just a 2 by 2 matrix. So the ijth element of this reduced density operator is going to be found in this following fashion. You take rho, the original matrix, I, K, J, K. I'm tracing out the second qubit. So the second qubit is in this location K. And I take the sum over all K's. So this is how I define an element in the reduced density operator. And by this fashion, I can find out what the, if I were to implement this on a maximally entangled state, let's implement this on a maximally entangled state. Let's find the reduced density operator for a maximally entangled. So a maximally entangled state, the Bell state is this. So if I trace out the second qubit, tracing out the second qubit really means if I implement this formula over here, just go home and implement this or code this on the computer. It's very easy. You just effectively what you're doing is you're taking the sum of this term with this term, sum of this term with this term, this term with this term. Okay, that's what you're actually doing. For example, rho A 0, 0, the first topmost term is going to be rho AB 0, 0, 0, 0 plus rho AB 0, 1, 0, 1, which are just these two terms over here. This term is this term, this term is this term. So you just add these terms. So rho 0, this 0 is this 0. This 0 is this 0. And you, first of all, you take both zeros here, and then you take both ones here. Okay. So this is how you implement this formula, you'll find out the reduced density operator. So you're effectively adding these terms. And when you add these terms together, of course, you get half, 1, 0, 0, half, which is maximally entangled, mixed. So the reduced density operator of a maximally entangled state is maximally mixed. Right? One measure of the entanglement is you find the reduced density operator, find the purity of the state, trace of rho square. If this is 0, then the original state has maximal entanglement. So now how do these do quantum state tomography? So it's easy to understand this in the context of single qubits first. I want qubit. I want to find these elements. So suppose let's take a simple example of a pure state. Let's just say a pure state is given by A. I'm using a polarization degree of freedom. So if I have a photon coming in, I pass it through a polarizing beam splitter, then H channel and B channel, and detectors. This is D, H, this is DB. This state comes in. Now, I create multiple photons in identical state. Naturally, they are created. So I have a stream of single photons coming in, all of them in the same quantum state. Remember, quantum information cannot be copied or cloned, but naturally, you can have a stream of photons coming in, all identical, identically prepared. So, you have statistical outcomes. So, you have n photons coming in. Some of them will take state, some of them will take state. And then you normalize. Number of clicks divided by the overall clicks. So you find statistics of this detection. And from the statistics of this detection, you compute the probabilities. If you have large number of photons coming in, the probabilities will follow these statistics. So, A, if I take this quantum state psi and I find the overlap with H, this will be the probability, roughly the probability that I get of this detector H clicking, right? And this overlap of psi with H is A mod square, isn't it? So the initial quantum state overlap with the horizontal polarized state will give me this, the probability that this detector clicks. Now, if I find this probability PH, this probability is A mod square. So A mod will be equal to this experimental observation. Likewise, B mod will be 1 minus PH. Right. So we're looking at the statistics of the outcomes from this beam splitter, which the horizontal vertical analysis beam splitter, which has a horizontal output and a vertical output. I can figure out what the coefficients A and B are. Remember, I'm talking about pure quantum state just for the means of understanding. But the quantum state also has a phi part. Sorry, where the B here. It also has a phi part, so your tomography is still incomplete, even for the pure state, because you need to measure phi. So how do you measure phi? How can you measure phi? So the experiments that I've done are insufficient. They cannot tell you what phi is. Yes. Sorry?
I mean, by using interferometric measurement.
No, this is all that you have. You can don't want to just have one beam splitter. You can have other components, but just one beam splitter. What can I do to measure this phase phi? Because without this phase is important. It cannot be just rubbed into the carpet and ignored. How do you find this phi? What kind of measurement can you do to find out this phi?
I think we are going to measure already this. I think we are separating if there any chance. We are measuring that already.
Fine.
Yeah.
We're not measuring phi because we're measuring A mod square and we're measuring this mod square. This mod square is independent of phi. But phi exists. When you take the mod square of all of this term disappears. But this term is there in the quantum state, so you want to measure it. How do you measure it? Quantum state amount, how do you measure it? So one way is to use a beam splitter which has two other kinds of outputs, which has a D and an A output, or a left and right separate polarized output. But these beam splitters are not available in the market. They're hard to build, I think. So what you could do, mathematically see, first of all, let's see what we can do. If I were to take the quantum state psi and project it onto cat B, let's see what happens. So instead of projecting onto cat H, let's project it onto cat B. That's what it is. Cat D is, I defined yesterday, cat D is plus coefficient. So let's do this. So A cat H plus B phi cat B and bra D. So okay. So this gives me 1 over under 2 A plus B phi. Right? Now if I were to find the modulus square of this, which is the probability of measuring B. So suppose I have this hypothetical beam splitter that can split into D and A channels instead of H and B channels. Let's see what happens. So the square of this is 1/2 modulus square, by the way, A star plus B star E minus I phi multiplied by A plus B E I phi. Let's see what I get. Half A mod square plus B mod square plus A star B E I phi plus A B star E minus I phi. This is A plus B square is 1, right? Plus 2 A star B cos phi. Okay. Now, in my original description, A and B are real numbers. A and B are real numbers because here A is a real number, B is a real number. All the complex part has been incorporated into this. Right? Any other global phase does not matter. So A and B have to be real in this description. All the complex thing is over here. Right? So the probability, this probability is half 1 plus 2 is the cosine phi. Now, if I have a beam splitter, by the way, such a beam splitter does not exist. So let's do a thought experiment. If I have a beam splitter, first of all, I do a beam splitter horizontal vertical, I get A, I get B. Now I do a beam splitter, I have this photon coming in, I have a beam splitter that has two outputs, a D cat B channel and a cat A channel, two detectors. I find this PD, correct? When I find a PD, I already know A and B from a prior experiment. So I have to do a series of experiments in quantum state model. I already know A and B from a prior experiment. Can I use this outcome now to determine phi? Right? Because PD equals this I measure experimentally. I already know AB, I can measure phi. Correct? But the problem is that the cosine function is periodic with a period of phi. So if phi is plus 30 degrees, I want to choose between plus 30 and minus 30 degrees. I can't do that with this measurement. So I also need to verify the sign of phi, whether it's positive or negative. Right? So I have already done 2 experiments with once with a horizontal vertical polarizer analyzer, now with a diagonal and diagonal. I need another experiment. Because I have 3 parameters A, B, and phi that I need to kind of, and I need to do another experiment. It's insufficient to just use the I know what phi is, but and I'm able to know the sign of phi. So I'll do another experiment in which I project another beam splitter, hypothetical beam splitter that can project onto left and right circular polarized light, PL and PR, where L is given by, for example, 1 over under 2 H plus iota T. It does not exist. It's not available in the lab. At least as far as I know. So we have to do something else. But this is a thought experiment. Mathematically it's correct. This is how we want to do it. So, we do another experiment. So if I were to find out the overlap of side with L and take the mod square, I get 1 half 1 minus 2ab. Oh, sorry, 1 plus 2ab, I think sine phi. That's what I get. If I do the calculation. Do this as a homework, please. So now I have, in one experiment I get cosine phi, in another experiment I get sine phi. Now I can tell phi. Now I can determine phi unambiguously. Because I have cosine and sine. I know what quadrant does phi have in. So I can unambiguously tell phi and I can completely determine what the pure quantum state is. So now we do a series of experiments. These series of experiments form the routine, the experimental technique of quantum state tomography. Now, so what am I effectively am I doing? If I look at this from a geometrical perspective, at the blocks here, at H, at V. My state lies somewhere. I don't know what the state is. P, some point P. So in one measurement, I choose this axis, HV axis. So I take this axis. In the first measurement, I have taken a horizontal vertical analyzer, which really means I'm finding the projection of the state onto this axis. Okay. That's the first experiment. What does tomography mean? You all know computed tomography, CT scans. When you go to the hospital, you do CT scans. So you have an object and you find 3-dimensional structure of this. And you take an image from different angles. Your camera goes at different angles, and then from all your 2-dimensional images, you reconstruct a 3-dimensional image. That's computed tomography. That's exactly what we're doing here for qubit, for the photon polarization. So you kind of project, in the first experiment, project onto this axis. In the second experiment, you project onto the BA axis. This is this is the, you project onto the BA axis and the equatorial plane. So you find one component of P, then you find another component of P. But then you need to know whether your phi is positive or negative, which side is it. So you project onto the third axis. With the left, right. So when you do all of these projections, you kind of completely determine where this point is on the hemisphere, whether it's here. You do the sequence of experiments with different kind of polarization analysis, but they don't exist in lab. So one way of, the Heisenberg and Schrödinger picture of quantum mechanics. And so what we're doing is we're changing the measurement basis. We're changing how we measure the photon, or changing the basis of measurement. But it's hard to change the basis of measurement because such polarization analysis don't exist. So why not change the state itself so that it reorients it with the new basis? So instead of changing the measurement basis, instead of changing the operator, let's change the state. So in one experiment, so now quantum state tomography proceeds in the laboratory as follows. Quantum state comes in. Oh, excuse me. So, the quantum state comes in. Sorry. You have two different kinds of elements. Followed by a polarizing mean splitter, which has an H channel and a B channel output, followed by your detectors. So this polarizing beam splitter exists and is available. Now these two objects, one of them is called a half wave plate, the other is called a quarter wave plate. Okay. Now what the half wave plate does is that it's a rotator. It rotates the polarization state. So when you want to measure in the dA basis, you just rotate the polarization of the photon so that it coincides with the HV basis. This is a quarter wave that it converts horizontally, diagonally polarized light into circularly polarized light. So these two wave plates, they can be rotated at different angles. They change the quantum state so that your quantum state is now inclined or aligning with this analysis. So instead of changing this measurement basis, we change the state in a predetermined way. So these quarter wave plates have angles H and Q. And the scheme is as follows. If I want to measure in the HV basis, this is QH, 0 degree, 0 degree. If I want to measure in the dA basis, this is 45 degrees, this is 22.5 degrees. If I want to measure in the LR basis, this is 45 degrees and 0. Alright, so by changing the angles of the quantum state and half wave, you can reorient the quantum state to do what I described in the thought experiment. And this is how you measure the entire density operator, not just the quantum state, but the density operator. Okay, so this is all that I had about quantum state homology. Eventually you will get a density operator, big, with all the elements in it. And I will show you some examples of that today. So I'm building up some background for understanding how photonic quantum information processing is done. I've described tomography. Okay, so you do a series of experiments on your photon. You just change it. First of all, you're looking at the state like this, and you turn it around, you're looking at this, but instead of turning around, you change the state itself. The two pictures are equivalent. Just like the Heisenberg Schrödinger pictures are isomorphic. Any questions?
You like perform this like one by one.
One by one. You do a series of experiments. Just look at this from a perspective of linear algebra. You have parameters that you want to find in your density operator. So you suppose you have two qubits, you have 15 independent parameters that you want to find. So you need to do 15 experiments for that. Anything less will give you an underdetermined system. You need at least 15. In practice, you get more experiments than you actually need. You have an overdetermined system. And then you use a minimization routine, probably machine learning or some other techniques that I will show to reconstruct the density matrix. Because the density matrix also has to be legitimate. There are additional constraints by the physics. The density matrix has to be trace one, it has to be a machine, it has to be positive matrix.
In effect, you are measuring the coefficients of the Pauli matrices by projecting them on different axes.
Exactly. Imagine the coefficient of the Pauli matrix. So the Pauli matrix description for one qubit and for any qubit you can decompose your density operating terms of the Pauli matrices.
I have a question. You said that you need 3 different experiments in order to get the final everything base. But if you use only one and third experiment, you can get the since sign, you can get the both sign and the phase. Am I right?
So you get sine phi. Suppose sine phi is 0.5. Suppose. But two values of phi will give this 0.5. One is 30 degrees, the other is 180 minus 30, 150 degrees.
Okay.
Because of the periodicity of the trigonometric function, you need to do an additional measurement to distinguish between 30 degree and 150 degree. So in order to find out where the point lies on the 4 quadrants, you need to do both sine and cosine. Or you need a tangent element. Alright, so any more question about quantum state tomography and we move on to our first element? Yes, please.
So in general, we can use Hadamard gates to discriminate phases. So are these how we implement Hadamard gates in labs?
Hadamard gates are implemented by Bean splitters. So Bean splitter implements a Hadamard gate. These are rotators. These are unitary operators which are rotators. So a quarter wave plate and a half wave plate is a rotator. So if you look at this scheme here, this is a measurement scheme. This is doing a projective measurement. If you look at the projective, quantum mechanically, what are we doing is we are finding we have a measurement operator, which is MHV, which is ZH. This is a measurement operator, or also called a polarization operator. So what we're doing here is we are measuring the expectation value of this operator for the quantum state psi. Okay, so we are measuring this thing. It's a von Neumann projection operator. This is what we're measuring. These two objects here, they are not Hadamard gates, they are rotation operators. And what kind of rotation operator? It depends upon the angle h and the angle q. They have their own unitary matrices. This is a unitary matrix for this and a unitary matrix for this. I can write on the unitary matrix as well. So my half wave plate, the unitary matrix for this will be, I think, cosine 2h, sine 2h. I think I've written minus sine 2h, or sine 2h.
So they can correspond to Hadamard gate for a specific
For a specific. Only for a specific. Best way to implement Hadamard gate is to Bean splitters. Any more questions? I love questions. I think I can feel that you are awake. and you're not bored. Yes, please.
This is only polarization and coordinate qubits. I mean, the real thing for polarization and coordinate qubits, we are using half-wave plane, quarter-wave planes, but what about other types of encoding? Like photon encoding?
Photon numbering.
Like, let's say you are encoding photons by using different paths instead of polarization. So what could be the optical elements?
So there could be, so if you have detectors in different paths. So one possibility is what I know would be the best approach would be to correlate the path with the polarization. That's what normally is done. Correlate the path with the polarization because polarizations are easier to measure. Unless you have a detector which measures the number of photons as well, with techniques such as finite boson sampling. So there are other more complicated ways, I'm not terribly sure of them. But this is how generally you want to do this in a lab.
But eventually you have to use
Or you could use cameras. Is one possibility is to use cameras as well, CCTV cameras to find out where the photon is coming. Position sensitive cameras. Yes, please. So now I'm going to shift gears a little bit. I'm going to talk about algorithms. Two kinds of algorithms that I'm going to present to you. One is Deutsch-Dosa. Have you seen Deutsch-Dosa algorithm before? Yes or no? No. So let's give a brief overview of an algorithm. So when you talk about quantum information processing, the promise of this accuracy is, let's do an example of the quantum computing algorithm, two examples. Very quick examples to show you how all of this connects together. The first algorithm that I'm going to show you is a user's algorithm. It's not used much, but it really shows the power of quantum mechanics and quantum information processing. And we can do this with photons as well. So the Deutsch-Dosa algorithm, one of the earliest algorithms that was invented. Deutsch-Dosa. Now what does this algorithm do? The algorithm is kind of, it separates out between two kinds of possibilities. Suppose I have a function f, and this function acts on 0 or 1. So it acts on x, where x is 0 or 1, and gives me output y, where y is 0 or 1. Okay? And the function f is of two kinds. One is a constant function, and the other is a balanced function. What does it mean? For a constant function, f of 0 is equal to f of 1. This is constant function. And it could be either 0 or 1. The value of the function would be 0 or 1, but it's equal for the two inputs. And a balanced function is when f of 0 is not equal to f of 1. So these are the two kinds of functions f. Now, I want to distinguish between these two functions. So I have some state in a computer, 0 or 1, and implement a function on it, and there's an output. So I want to determine what kind of function is it. So there's some computer, some information processor that implements f, it inputs x, outputs y. So in order to tell whether the function is x, constant or balanced, first of all I need to shove in x equals 0 and see what the output is. And then in the next experiment, I need to input x equals 1 and see what the output is. And then compare two results. Then I can determine whether I have a constant or a balanced function. Now, quantum mechanically, you don't need to do two experiments. With a quantum algorithm, you can do it just once. So naively, if I input a quantum state x, and if I implement the function f of x, and then in another experiment, I input a function ket y, and I see what the output is, I can determine whether the function is. But I need two runs of the experiment. Once with x input, the other with y input. But in a quantum algorithm, I can do both things at once because of superposition and because of the parallelism that quantum physics offers. Now, how do I make a circuit for this computation? Now, I'm still using the circuit model here, but it kind of brings home the idea of what a quantum algorithm looks like. So suppose I have in quantum physically, in quantum algorithm, I kind of need two qubits for this. One is my working qubit, the other is an ancillary qubit. An ancillary qubit is an additional qubit, which helps in the computation, but it doesn't matter in the end. So what I do is I take two qubits, both of them in the state type 0. So second qubit is in the state type 1. Sorry. And then I have my gate on both qubits. And then I apply the function. And then I define a new function. Let's call this function UF. So the function is now encoded in a quantum circuit. So this is a 2-qubit gate. Finally, I put a Hadamard gate here and a Hadamard gate here. Now, a 2-qubit quantum algorithm. This is the first example, kind of introduction in this course. Let's see, of a 2-qubit quantum algorithm. Notice the similarity between the marks and the interferometer and for a single qubit. So I had a Hadamard gate, the phase gate, followed by a Hadamard gate. So I have two Hadamard gates in the beginning, or multiple Hadamard gates in the beginning. They create a superposition. Something happens, and then I collapse with the second Hadamard gate. There is a general scheme of quantum algorithms. It's also valid for the Shor's algorithm, for factoring, and so on. So now, what does the function UF? What does the unitary operator UF do? The unitary operator UF implements the function f. How does it do that? In the following fashion. I have two inputs, two qubits, x, y. Each one of them is 0 or 1, UF. So what this function does, it does nothing to the first qubit. And to the second qubit, it takes y, exclusive OR with f of x. Okay? Exclusive OR is the same as control not. Do you want me to explain exclusive OR or the truth table for exclusive or not? Just raise your hands. No, it's fine. Okay. Now, this is the algorithm. Now let's see what happens to the state. So I input ket 0, ket 0, 1. The first Hadamard gate and the second Hadamard gate. The first state goes to ket 0 plus 1 over 2. Second goes to 0 minus 1 over 2. Right? Then I just break this up. 0, 0, minus 0, 1, plus 1, 0, minus 1. So this is my quantum state at this location. Remember, so far I'm not measuring anything. I just have built the circuit. Before found anything, built the circuit. And now my quantum state looks like this. Now I want to implement the function. So the function does. So I implement the function is to a unitary operator, UF. So I just go to the next page, half, get 0, 0, exclusive OR with f of 0, minus 0, 1, exclusive OR with f of 0, plus 1, 0 plus exclusive OR 1, minus 1, 1 exclusive OR with f of 0. Okay, I just implemented this function over here. What this function does nothing to the first qubit. The second qubit is what's in the second qubit, exclusive OR with the application of the function on the first qubit state. Like a control NOT gate. Now the exclusive OR of 0 with anything else is the anything else. Right? So I can write this in the following fashion. 1/2 0 f of 0 plus minus 0 1 f of 0. Okay. What I could do is I write this as 1/2 x 0 and so I combine these terms, right? I can factorize out the first qubit and get f of 0 plus 1 cancelled with f of 1 minus 1. Alright. Now let's look at this term. If f of 0 is 0, this is ket 0 minus ket 1. If f of 0 is 1, this is ket 1 minus ket 0. So this is 0 minus 1 or 1 minus 0. Likewise, this is 0 minus 1 or 1 minus 0. What I've written in yellow, the state of the second qubit is 0 minus 1, ket 0 minus ket 1 or minus of this, negative of this, ket 1 minus ket 0. And whether it's positive or negative depends upon the value of this. So I can write this in simple form as follows, in following fashion. 1/2 ket 0, 0 minus 1, correct? Okay, minus 1 raised to power f on 0 plus alright. Now, so this thing is a number, just a number. And it's equal to plus 1 or minus 1. It's a number, it's not a quantum state, it's a scalar. This thing is also scalar. It's a number, it's a phase, plus 1 or minus 1. So this can move around anywhere. It can be associated with this qubit or this qubit, doesn't matter. what I could then do, I could rewrite this as just for convenience. I can factorize out this part. So zero. Sorry, this is kind of converted a little bit, so I write this as 1 over root 2. And 0. Got it? Second qubit, first qubit, separable, everything is separable. Now the second qubit, this qubit, Caesar had a mod. So only interaction, the two qubit correlation occurs up to this point. Second qubit now sees an interaction. And it just, after this interaction, 0 minus 1 becomes cat 1. You don't look at this any further. Just ignore it. So this ancillary qubit has come in as a mother guard, as a helper. It just came in, kind of picked up a phase. That phase got transferred to the first qubit. Just ignore it. Okay, it just has come in as a helper and you just ignore it. That's why this is an auxiliary qubit. So you need two photons here, by the way. Now, the state of the first qubit over here, since the state is separable, the state of the first qubit is the same. Now this Caesar Hadamard. The first qubit sees its own Hadamard. So now let's just focus on the first qubit. I just focus on this term here and apply the Hadamard gate to this. On the first qubit. So 1 over root 2 minus 1 is correct for 0. Get 0 plus 1 over root 2 plus minus 1. Therefore 1. 0 minus 1. Let's kind of do some simplification. Alright. This is the state of the first qubit. If the function is constant, which term survives? The function is constant. Which term survives? Survive means it does not disappear. The first one. First one. This term survives. This term disappears. This term just goes away. So your first qubit is left in the state cat 0. And you can measure this with perfect certainty if you have a beam splitter that can project in cat 0 and cat 1. So if the first detector clicks after a beam splitter, then this is constant. If the other channel clicks, which means the cat 1 channel clicks after beam splitter, then the function is balanced. Okay. So what you do here is you in the circuit here you put a beam splitter that separates out into cat 0 and cat 1 channel. If sorry, how can I manage that? Sorry. So I have this detector here. If this detector clicks, the function is constant. If this detector clicks, the function is. So now, at the end of this experiment, I'm back to the computational basis, something that is easy to measure. And the projective measurement is to my advantage now. Generally, projective measurement destroys the state, but now I'm using projective measurement for the readout. These could be two photons prepared in horizontal, vertical, Hadamard gates supplied by green splitters. We still don't know how to pair 2-qubit gate with photons, but this is what it is, at least in the circuit model. You apply Hadamard gates, you have detectors here for photons, you can tell whether the function is constant or it's balanced. But this algorithm, if you have 1 qubit function acting on a single bit, these are 1-bit functions acting on 0 or 1, but you can have a string of bits. You can have an n-bit register. So you can have 2 raised power n strings in that register. So this would be n qubits coming in. So you have a Hadamard gate on all of them. And you can tell whether the function is constant or balanced. Now this is a useless algorithm in the sense that it does not achieve much from an application perspective, but this kind of sowed the seed for quantum information processing, that this is really important and this is something worthwhile to be explored. I think we can take a 10-15 minute break. After that, we'll do the Grover algorithm. All right, so let's get started. Kind of decided to change things a little bit. I will do Grover search algorithm tomorrow morning. Because I really want to show you some experimental results today. So tomorrow morning we have to do some more work to do understand cluster state quantum computing. Anyway, so I do want to do quantum computing. This work that I'm going to show is about quantum information, concepts in quantum information and how they can be implemented with single photons. Now this is work that we do in Pakistan, and I think this is mostly for educational purposes, but it kind of is also a test bed for research, and we also do research on with these ideas. So let me give you an overview in this 1 hour of how we use single photons, how we produce single photons, how do we look at their different degrees of freedom, the polarization and the power degree of freedom, how do we measure them, and look at basic concepts. One thing I also was not able to do is discuss quantum erasure. I wanted to do it mathematically, but maybe that's I can do touch upon this tomorrow, but let's see. So, all right, so let's. So these laboratories were developed by these students from engineering and quantum physics. All of this work is done by these 4 students and 1 student over here. I also have a graduate student, an undergraduate student, sorry, who's now doing a PhD in Rochester University. Hamza, the middle person, is doing a PhD in Oxford University. Faizan is doing a PhD in, I think, University of New Mexico. Bilal is going to Edinburgh for a PhD. Do you have a pointer here by any chance? If not, it's fine. This is a picture of the single photon laboratory. One picture with students working on it. And all of these are different kind of elements that implement quantum processes. So we use this laboratory to demonstrate different ideas: quantization, superposition, entanglement, quantum interference, quantum uncertainty, and the process of measurement. Students on the side also do other spectroscopy experiments. They do solar spectroscopy. They also do bright sky spectroscopy. They also do spectroscopy from atomic papers, rubidium papers, and so on. So we have a complete ecosystem in our laboratory in Pakistan where we expose our students to these different ideas. Now, if you look at the overview of the single photon laboratory, this is what it is. In purple, thank you very much. Bill, thank you very much. So, laser light comes in, and 4 or 5 nanometers. It's a continuous wave, spectrally pure laser. And there are 2 crystals here, BBO crystals, beta barium crystals, that are cut in a special orientation. And their 2 optic axes are orthogonal to one another. And they are glued together. With index matching fluid, they are put placed close together, very close together. And they're very thin. Each one of them is about, I think, 2 millimeters thin. And the optic axis is cut in special orientation. And 3 beams emerge. One is the pump beam itself, and 2 beams of single photons. These 2 photons are entangled in time, entangled in polarization, and entangled in K, in their momentum. So everything, all 3 degrees of freedom are entangled. We use the polarization and the time degree of freedom. And then they kind of see different kinds of elements. This is the general scheme, by the way. Half-wave plates, quarter-wave plates, polarizing beam splitters, as I mentioned. And then detectors, 4 detectors, 2 for this beam and 2 for this beam. A prime, B prime. These are single photon detectors. They are avalanche photodetectors. They trigger on a single photon, so they can count single photons. And then they produce an electrical signal, which are represented by these 2 arrows, and they go to counting modules, single photon counting modules, and out of these modules emerge these pulses. So these pulses then go into our electronics. We have made special electronics to kind of shape these pulses. These pulses don't look very nice, so they have to be shaped a little bit, and then count the pulses, and then we put everything in a register and transmit the data to the PC. And the PC does all the graphical analysis and all the statistical analysis. This is a photograph of these are the big boxes are the detectors. So everything's in free space, and the photons then are collected into these optic fibers using fiber space couplers. They are collected into these optic fibers, multimode fibers, and they are fed into the single photon detectors. And from the detectors emerge these pulses of this shape, and this is our electronics box. It's an FPGA. Everything is programmed in the FPGA, and then the data goes to a computer. So you count the number of detections on A prime, B prime for various kind of experimental configurations. Now this is a scheme in a different view. Laser. The laser beam is optically steered. Then you have a half-wave plate that changes the polarization of this laser beam and a pair of BBO crystals. The pump beam is blocked, and then 2 photons emerge. You have irises for further alignment, and then you can have half-wave plates, quarter-wave plates. In different arms, you can have detectors and a polarization beams reflecting. You can ask me a question anytime. Well, we can. I'm just showing you a concept. There are different kind of experiments. I'm just showing you the concept here. Now, this is everything put on an optic. This is a real photograph. Very simple. Very easy to build. Laser, mirror, crystals. There's a stream of nitrogen coming on to the crystals. And these are all your elements. So, some student was asking me about this is what a quarter wave plate looks like. It's a thin crystal, it's placed in a mount, and this is controlled with a motor, and the motor changes the orientation of this. As everything is computer controlled. And change the orientation of the half wave plate and quarter wave plate angles using these motorized stages. These are motor controllers. These are, everything is then coupled into the optic fibers, and this then goes into the detectors which are placed in a black box. And you do all the experiments and there is no light in the room, everything is to be dark. Or use green light because you put some other filters before the detector, so only long wavelength light goes into the detectors. So this is a typical pulse from single photon detector. Right, this is nanosecond time scale, has about 50 nanosecond major lobe and then some ringing. So you have to do some impedance matching and some pulse shaping, high speed pulse shaping to control. And then these are your pulses, you count these pulses. So the duration of these pulses is about, and this is, we can control the duration of the pulse from 3 nanosecond to about 20 or 30 nanoseconds. You can program our FPGA to control the pulse width. Now we use different kinds of detectors. Each detector has some dart counts. So even when the lights are off, you get some counts. These counts are per second. Just have some counts for the different kinds of detectors that you buy. And you need to know the dart counts. And there's some dead time, which means that a photon comes in, it will not be able to register the next photon before a 50 nanosecond time delay. That determines the maximum brightness of photons that you can put into your detectors. And there's some pulse width that comes from the detectors, which we further control using our FPGA. So once all the data comes, so this is the FPGA board. We program it using some very VHDL programming in Verilog. Our students do it, I don't know about it. So then they kind of put everything and all the counts, the A counts, the B counts, the B prime counts, A prime counts, and the coincidences. Coincidences really mean that two coincident detection on A, B prime, and so on, and threefold coincidences as well. So all of this data is put in a header. With a header, this 10 byte data set is then given to the computer after clock interval. We also characterize our fully characterize our time correlation unit and so on. So we have the fidelities and the integral non-linearities for all of our electronics. We fully characterize that. So what really happens how do we have single photons? So let me describe a little bit about single photon. What is meant by a single photon here? Single photon really, so there are two ways of doing a single photon. One is you have some emitter of photons and you turn on a switch and it produces one photon when you desire it. So you have a switch, some kind of laser pulse, some kind of electric field, or switch, and it deterministically produces a single photon at your will whenever you desire. We do not have a two single photon source here. However, what we have here is two single photons are being produced, or a beam of entangled photons are being produced. Whenever there is a photon in this arm, it heralds the production of a photon in the other arm. Heralds means shouts or signals. So whenever there is a photon in this arm, there must be a coincident photon in the other arm at the same time, simultaneously. So we only look at those photons here that have a twin in the other arm. So you only look at those experiments where there are coincident detections. So this stream of photons, under the condition that there is a concomitant, there is a simultaneous photon on the other arm, forms effectively a source of single photons. This is called a heralded single photon source. Okay? So we have a heralded single photon source here. And it's non-deterministic. We cannot control when the single photons are coming because the process of photon generation is highly non-linear and you cannot determine when a pair of photons is going to be produced. However, in order to have a high photon count rate, you need a large pump beam with a high power. We use a relatively high power, 40 to 50 milliwatt power, so that we have sufficient number of photon pairs that are coming out, so that we can do our experiment in reasonable amount of time, which is perhaps half a minute or 1 minute. Okay. So this is a pseudo single photon source. But these are single photons, and this is really quantum light. These are numbers quantum states, and we can prove that, and that's what I'm going to show you. That these really are single photons. Even though heralded, they are single photons. And the photons that come here, conditioned upon the simultaneous arrival of another photon and the other arm, they are single photons. And this is quantum light. So let's say the different kind of light. By the way, one of the arms is called the Euler arm, the other is called the signal arm. What happens is when you have two crystals, so this initial half-wave plate changes the input polarization. What half-wave plate is just a polarization rotator. So the input polarization is adjusted, and there are two crystals. One of the crystals converts cat B into HH. The other crystal converts cat H into BB. So if you have a photon coming in, which is in a superposition of B and H, it's a diagonally polarized state. And that diagonal polarization is controlled by this half-wave plate. So you input diagonal polarization into this pair of crystals, you get a linear superposition of HH and BB. You cannot tell which of these crystals are the photon pairs coming from because they're so thin. They are simultaneously produced within the coincidence time window. Hence, they're entangled. So you produce a superposition of AHH and BB. These two photons are therefore in approximately a balanced state. And we need to state in order to verify this. So then they fall on the detectors. The process can be described by classical optics, non-linear optics, by the way, in which a single photon with a particular frequency and wavelength comes in, two photons are produced. Angular momentum is conserved, linear momentum is conserved, energy is conserved. So if this wavelength is 400 nanometers, these two wavelengths will be 800 nanometers each, plus minus some deviation. Okay, and they will be emitted at certain angles, a range of angles. That range of angle is determined by how this crystal has been cut. So there is a matching angle. When you order the crystal, you have to define what is the angle at which these beams are coming out. And when you know what the angles you desire, you tell the crystal manufacturer that I would like this crystal to be cut at a certain axis, at a certain, the face must make a certain angle with the optic axis. And then you use classical optics equations, Sabieh equation, and the equations that we birefringent optics to find out what your matching angle is. So this is some exercise in classical nonlinear optics which students and researchers can easily learn about. So you have to order the crystals carefully. So when the pumping comes in and these two crystals close together, mated together, they produce two beams of photons coming out in cones. And then you can also image these cones. So this is an image of two cones that are very close together, almost they merge together. So these are entangled photons that are coming out and they're imaged on the CCD camera. Okay. So you can image these single photons coming out. You might argue that I'm calling them single photon, but there needs to be a test to verify that these indeed are single photons, and we will describe that test in a minute. So then we need to do some kind of alignment. Students spend 80% of the time doing alignment, 80 to 90% of the time doing alignment. The data just takes 1/10 of the time. Otherwise, they have to learn all the quantum optics and the quantum mechanics that we slightly covered in this course. So, they spend some time on alignment. Alignment is done using back propagation. You have instead of a single photon detector, you replace this with another alignment laser. You just shine light all the way onto the BBO crystal through the two arms, that it hits on the center of these crystals. Then you would know that this entire arm is aligned properly and so on. Now, initially, how do you test? alignment. So if the initial pump beam angle, you vary the pump beam angle, no change in the counts should be seen. So, however, initially there is some modulation of the counts. So these are single counts and these are coincidence counts. Here we have single counts and coincidence counts. So if everything is properly aligned, changing the pump beam angle should not change the counts. And so when we have a data of this kind in which the counts are independent of the pump beam angle, you achieve an initial alignment. And you can show this mathematically. By the way, I have a book that describes all the processes in a bit more detail. I'll show you on the internet where the name of that book. So how do we tell that these are single photons? Now there are different ways of distinguishing between different kinds of light. One way is to look at the statistics of detection. The statistic of detection means you just have a time interval and you count the number of photons coming in and the time interval. Now, so if I plot the number of photons and the probability of detection, I can get three kinds of light. One is light from a laser, a very nice laser, coherent laser. The statistics of detection will follow the blue curve. And this distribution is a Poissonian distribution. Poissonian distribution, in which the mean and the width are related through this relationship. The width of the standard deviation is equal to the square root of the mean. This is a Poissonian distribution. Many natural processes follow Poissonian distribution. For example, if you have a resistor and you find the noise of that resistor at a certain temperature, which is called Johnson noise, that will show Poissonian distribution. If you have a radioactive sample and that radioactive sample is giving off radiation, you look at a detector using a Geiger-Müller count, look at the statistics of the radioactivity. It will be Poissonian distribution. If you are in a barn with a tin roof and you look at rain and count the distribution of the rain drops falling on the tin roof, it will be Poissonian distribution. Many natural processes are Poissonian. A pure laser with no phase jitter, no phase noise will be Poissonian. However, if you have chaotic light sources, classical light sources like these LEDs or incandescent bulbs or the sunlight, the spread will be bigger than Poissonian sources. So this is called super Poissonian statistics. But quantum light, if light is quantum and it's what is called bunched or anti-bunched, then the statistics will be sharper than Poissonian light, and you get this red curve. That's sub-Poissonian light. So light is quantum. We have produced quantum light or quantum state of light when you have sub-Poissonian statistics. So we're looking at the detection statistics, you can tell whether you like it Poissonian, sub-Poissonian, classical or quantum. Classical light, the best classical light is Poissonian, nice laser source. In quantum optics terminology, it is called a coherent light source. Now, a little bit about statistics. Now, there are two things about light. And when you do these experiments, two things come to the mind. First of all is the statistics of the photon in a light beam. The second is the statistics of the detection process. Because light beam is coming in, the photons have certain statistics. But then your detectors are imperfect. Your detectors have their own statistics. So when light falls in or photon falls in, it may click or it may not click. There will be some efficiency problems. So two things come to mind. One is the intrinsic statistics of the photons, and one is the detection statistics. So suppose I have a very weak laser source. Now one might argue that one way to produce single photons is by attenuating light. So you have a laser and you put a attenuator, neutral density filter, one after the other, one after the other, one after the other. So that you have a very dim light source, a strongly attenuated light source. And that eventually you will get down to the graininess of light and we will see single photons. But that's not possible. That is not quantum light. That's a very weak quantum light, non-quantum classical light source. Coherent light source is a very small value of alpha. So if you have classical light, even if it's weakly weak and it's highly attenuated, and you look at the photo counts, the statistics will still obey corresponding statistics. But we want some corresponding statistics. Normal light is, so if you look at this scheme in which you have coherent light, the one way of looking at the photons is by how further they are apart in the beam. Suppose you have this weak light source, highly attenuated, and you break up the beam into these small chunks. And there are some chunks in which there is a photon, and there are other chunks in which there is no photon. So the photons are coming in sparsely after long intervals of time. That's what the weak light source is. So now some of these chunks are empty and some of them have a photon. So this is an example of a coherent light source, which is classical. Okay. This is an example of a quantum light source in which these photons are equally spaced in that beam of light. A perfectly anti-bunched light source. This is quantum, and this will demonstrate some Boltzmannian statistics. But this is just looking at the beam of light without any discussion of the photon statistics. If you have a sub-Boltzmannian light source like this, and you have imperfect detectors, bad detectors, then this anti-bunched light can also become bunched because of the photon statistic, because some the time you will miss a detection. So you need very high efficiency detectors to really see this kind of light. And this is the light that we want to produce. These are single photon states. These are anti-bunched photons. These will show sub-Boltzmannian statistics. This is the kind of light that we aim to produce. And this is not going to come by attenuating the light source, because attenuating the light source will give you something like this. Okay, so we really want to make single photons, which are called number states, Fock states with n equals 1. And if you really have single photons, then this statistics will show the Dirac delta function at n equals 1. So this based on peak. The normal distribution. That will be a true ideal single photon source. So we can look at the kinds of light by looking at the statistics of detection and by looking at the spacing of the photons in the beam. A third way, which is the more powerful way, is looking at the second order correlation function. I'm going to be describing it. Alright, so this is a summary. If my photon statistics is super-Boltzmannian, light is bunched, Boltzmannian coherent, sub-Boltzmannian anti-bunched. And we want to work with this scenario. Sub-Boltzmannian statistics, anti-bunched light, and these are the single photon states that we're looking for. But how do we distinguish between, in an experiment, we really want to do some measurements, quantifiable measurements. So we use this object, mathematical figure of merit, which is called the second order correlation function. Now, what is the second order correlation function? Generally, the first order correlation function, if you look at the first order correlation function, it's this quantity here. I hope you all know what a correlation function is and autocorrelation function is. It's some field, in this case, an electric field measured at some time, multiplied by the same electric field at some later time. And you take the average of all of these products of these electric fields with time, and then you normalize. This is a first order correlation function. But as you know, in optical experiments with photons, you do not measure electric fields. You measure intensities or photon numbers. You cannot measure electric fields unless you have some complicated electromagnetic CCD camera, street camera, or something of that kind. So you really measure intensities instead of electric fields. Intensities are proportional to squares of the electric fields. So Hanbury, Brown, and Twist, when they were doing observational astronomy experiments, they were looking at intensities from different light sources and correlating the outcomes. So they came up with this formula for which is second order, which instead of using an electric field uses intensities. So you have two intensities at two different times, and you take the product and average. This is the second order correlation function. And this is what we would like to measure for our light source. Now suppose beam of photons is coming in. Now I'm going to kind of connect this with the photon picture that I have described and experiments that I have described. A beam of photons is coming in, and we have a beam splitter, and there are two detectors B and B prime at the output. You would like to measure the correlation of counts between B and B prime. Coincident when tau equals 0. So we want to make coincident detections between B and B prime at the same time interval, within say 1 or 2 or 3 nanosecond time interval. Whenever there is a photon hit on both detectors, you see there is a coincidence detection. So you want to measure the number of coincidence detections at the same time, within the same time window. So in terms of probabilities, when you deal with finite sources like single photon, these intensities become probabilities. So the numerator, which is a product of two intensities, when tau equals 0, I2, I1 becomes the probability of both a detection and B and B prime at the same time. So the numerator becomes this probability of coincidence count between B and B prime at time 0. And then you normalize by the total number of singles on B and singles on B prime. So this is a measure of the second order correlation function for this beam of photons. Now, if you just look at one beam coming out from the BBO crystals, you predict that this second order correlation function will be greater than 1 or at least equal to or greater than 1. So it's Poissonian or sub-Poissonian, which means if you just look at one beam of photons coming out, light will be classical. You will not have the cheap single photon steps. Only when you have this second order correlation function in which you also condition upon a detection at A, will you have quantum light. So let me recap. I'm going a bit fast here. So let me do. So but this is important. I'm looking at coincidence detection between B and B prime on one arm of the two photons. I'm just ignoring one arm. So if I look at the second order correlation function, this turns out to be greater than or equal to 1. So it's super Poissonian or Poissonian and not quantum. I have not achieved single photon if I just look at one arm. If, however, I look at threefold coincidences, that is, whenever there is a detection on three detectors, A, and B prime together, given that there is a third coincident detection on A as well, so whenever there is a threefold coincidence, then I look at the statistics probability of threefold detected coincidence A, B, and B prime, and then I normalize. This number turns out to be smaller than 1. Okay, which means that when I am looking at heralded single photons, given that there is a coincident click on A, and in that subspace, I have single photons. In fact, for the ideal case, this numerator should be 0. Why? Why should this numerator be 0 for the ideal case? Because it's one photon. And one photon can go either this way or this way. One photon cannot be split. Right? A photon can go either B or B prime. A photon is indestructible. you cannot split up a photon as a linear optics that you're talking about. So one photon can go either this way or this way. So at one time, if you have single photons, there can be no coincident detection on B and B prime, given that there is a coincident photon on B. So this numerator should really be zero. So if you really have single photon sources, then this threefold coincidences should be a number close to zero. And if you get a number close to zero, then you have single photons. And now you want to do an experiment to find out this number, this second order correlation function for your light source. So if I would translate this into the numbers, because in real experiments, the probabilities become numbers. How many photons do you have? You counts. How many counts do you have in a interval of time? So if you translate this into number, this is what you get. This is a threefold coincidence, second order correlation function. You find this number and see whether it is less than 1 or greater than 1. If it's less than 1, you have quantum right. If it's greater than 1, you have classical right. If it's 0, you have single photon source. Perfect single photon source. Now, so we can do some basic experiments first of all before we measure the second order correlation function. We do some basic measurement, change the input polarization, and see the. Really, this is, remember day 1 when I talked about the photon coming in cosine alpha, cat H plus sine alpha, cat B. If I change alpha, I get some variation, some counts here, some counts here. I can change alpha, I can have all the counts go here, and I can have all the counts go here. So this is that kind of pattern that you see. This is a simulation, this is a real result. Yes.
You said that we cannot obtain single photon behavior when we ignore the bit around, right?
Will be right.
Bit what?
Please repeat the question.
You said that we cannot obtain single photon behavior if we ignore, if we just look at the signal.
Exactly.
But when you are explaining the second type of experiment, when we detect
This experiment.
yeah, in this experiment, you said that G0 is should be 0 because one photon cannot split into two, right? But it's true for the other. If we ignore the if there are still single photon cannot divide into two.
Right. So this experiment here is not single photon behavior, but any light, whether it's classical or quantum, will show this behavior that if you change the polarization of light and you have a polarizing piece filter, some of the intensity will go to one detector, the other will go to the other detector. So it doesn't matter whether you have single photons or not. So this is a classical result. This is a classical result. So I'm just showing here in this data set. I'm just showing that if I just look at this beam, if I change this polarization, if I just through this half wave plate, if I change this polarization,
I didn't ask this question for this data set. I'm just listening for the some phrase you used while explaining this. So if we ignore the RA and equals to RA, can we see single photon behavior?
no.
But if we have single photon going towards the detector B or it cannot divide it.
So we can.
So we should the separation between probabilities detecting E and B prime.
Right. So if we ignore arm A, we do not see then the second order correlation function that we're calculating is this one.
Yes, P, B, and B prime would be 0. So it is 0. So it's supposed to be correct.
Why is the B equal to, no, this will not be equal to 0. This will not be equal to 0. In fact, this will be equal to 1. P, B, B prime will be equal to PB multiplied by P, B prime because B and B prime are two independent events. There are two independent events. If you have probability for two independent events, then what's the total probability? Is the probability of each multiplied by the other. So this term will become equal to 1. If B and G prime are independent events, which are the case for classical light, not single photons, then this will be equal to 1. I will show you that this is equal to 1. This elementary data as well. Okay? This is 1 for classical light, for pure classical light, coherent light.
For quantum light,
For quantum light, it's 0.
it's 0, but you were saying that with this combination, we cannot confirm.
We cannot see quantum light. We have not produced quantum light with this, just looking at one arm.
Yes, but yeah, of course, we need the heralded scheme, but also if there's one couple coming, like they are coming one by one, still B and B prime coincidences are going to 0, right?
No, you have this bunched situation in which you cannot see one photon coming in at a time.
Yeah, in one situation, I mean, in the laser, yes, but in like SPDC, aren't they supposed to be one by one?
No. Well, let's find out what the correlation is. They're not one by one. This thing turns out to be equal to 1. Because you have not yet said, this is the kind of counterintuitive result. This is the counterintuitive result that I want you to show, that if you just look at one beam, one arm, you do not have single photons. You have light that is bunched. And
Quantum light.
no, it's classical light. It's classical light, it is bunched, it's just weakly attenuated. It's weakly attenuated classical light. Photon number state could be the alpha. If you look at the coherent state at alpha, it could be very small. It could be 0.1, it could be 0.3, it could be less than 1. But it's still coherent light. And you look at the statistics of detection, you can find out the second order correlation function here. And it's going to be equal to 1.
We are assuming
Yes.
these are coming from the slides coming from the SPDC.
Yes.
Right?
But when it's coming from SPDC,
Mhm.
let's say this is signal arm.
Yes.
Well, I-
It's not quantum.
It's still not quantum.
It's not quantum. Unless you do heralding. You need heralding for this.
When heralding, you are just making relationship with these arms with the other arm.
Only then will you have anti-bunch, right? Only then will you have second order correlation function less than 1. Let's see the result. Let's see the result. So this is something that is really important, by the way, and this is confusing, but it's how it is. So if I were to do, let's do next one, let's see next experiment. So if I do an experiment without any heralding, this is your point of just looking at one, this is the value of the second order correlation function. 1.110 greater than 1. Okay.
I mean, are they already anti-bunched? Like when
Single photon sources do not give anti-bunch light unless you look at both photons together. So light is not quantum unless you look at both of these two arms together. Right? So this is the key point.
But we can express state of one arm.
It is a coherence function. So get alpha with some factor here. Coherent light. I might be kind of forgetting this, but this is coherent light. So this is the equation operator. Cat 0, I think cat 0. And this is the Poisson distribution function. This is the state of this light, of this single beam.
How the other arm affect the behavior of that?
Because of entanglement. Because of entanglement, so you have that other arm. You see, two photons are coming up. If one photon, if you kind of detect one photon, it heralds or signals that there is another photon in the other arm. And the statistic of that photon will be subcorresponding. The second order correlation function of that second arm will be less than 1. However, if you ignore this arm, if you ignore the heralding process, the light is totally classical. It's coherent. It's the best classical that you can get. It is a very low photon count, but still the statistics will be corresponding, and the second order correlation which will be 1 or greater than 1. Okay. So now these are the experimental results, by the way. So second order correlation function without any heralding is classical. It's not quantum. You need to believe this. I mean, this is the second order correlation turns out to be this value. It's very nice. It's very nice coherent source.
You mean by heralding, there's still a heralding photon, but we are not measuring that.
Not measuring it. So we're looking at the statistic. So in heralding scheme, we're only looking at the statistics of what happens on the signal arm where there is a coincident either photon detection. If you ignore that in coincident either detection, then we just get a classical light source, coherent light source. Very clean, but it's still coherent. This number is close to 1. Okay, which really means that this numerator here is equal to PB into PB prime. Which means that if the pump, okay, let's do an experiment. If the pump power goes up, if the pump power and just using one beam, both PB prime and B prime will go up simultaneously, as in a classical experiment. That's why this number remains equal to 1. So it's classical light. It's not quantum light.
Not measuring the pump beam.
We can change the pump beam power.
Yes, I mean, but still, you're not measuring the pump beam, you are measuring the.
Right, but the down converted.
The down converted.
But they are coming from the pump beam. So higher the pump beam power, higher will be the flux of those down converted.
Yes, yes.
So you can increase the power of the pump beam, decrease the power of the pump beam, this number remains close to 1. Which means that this numerator is equal to the denominator. Which means that B and B prime are independent events. They are not single photon, because a single photon cannot be split. If it's a two single photon, then the numerator must be 0. Which is not. Okay? I hope I have convinced you. And in fact, there's no better convincing one can do than experimental data. Okay, so this is experimental data. Unheralded, non-single photon source, just one being the second order correlation function is this value. If you were to do this experiment with different coincidence windows, so these are the results that you get. These are the counts on A, counts on AB prime, AB prime. Now compare these threefold coincidences, 4 counts, 6 counts, 0.7 counts with RAB or R, right? Really minuscule, very small. And if I were to calculate the second order correlation function based on the threefold coincidences, this number is much smaller than 0 or 1. Right? It's much smaller than 1. In fact, this number is 22 coincidence intervals away, 22 standard deviations away from the classical quantum threshold. This is 340 standard deviations away from the quantum classical threshold. So this really is a single photon quantum source. It is a number state. Okay. So look at how far away are we from classical. How many, if you were to do these coincidence intervals in particle physics experiment, it's impossible to do such kind of experiments in particle physics. This high confidence that you have quantum, right? And by the way, why is this number not equal to 0? It should really be equal to 0. If you really have two quantum sources, it should really be equal to 0. But why is this number not equal to 0? Experimental problem, because it could be. Huh?
We are using timing of the
No. If the confidence window is smaller, then this number is also going to be smaller as it is over here. These are due to coincidence, accidental coincidences. Accidental coincidences really mean that sometimes it's possible to show you proper. Okay. Accidental coincidences means that it's possible that in the coincidence window that you're talking, two photons are detected, one on A and one on B, but they're coming from different down conversion events. So there's one pump photon that comes in that produces two photons, and then another pump photon comes in that produces a subsequent down conversion event, and the process happens so rapidly that these two coincidences in the coincidence window are happening from non-twins. Okay. So that's then there can also be accidental coincidence between dark currents and true currents. So all of these factors contribute to accidental coincidences. And given the coincidence window, you can actually determine what the accidental count rate is going to be. This is called statistics. So if we were to determine the accidental coincidence count rates, these are what accidental count rates are, and these are roughly equal to what we measure. So any deviation from zero, which is true quantum right, is primarily due to accidental counts and is purely explainable. So we have single photons here. Quantum right. Anti-matched. Second order correlation function close to zero. And if you make a plot of the second order correlation function with respect to tau, which is you can relay one of the lines from the one of the arm and kind of do a time dependence technology. So you see within the coincidence window, which is about 10 nanoseconds in this experiment, is plus minus 10 nanoseconds, 15 nanoseconds, the second order correlation will drops to almost zero. And this small deviation is due to accidental counts, and this large gap from 1 tells me how much confident I am of my result. Okay, so this is a single photon quantum source. And you need a second order correlation function experiment to demonstrate this. I hope I have convinced you. I can somewhat, little bit. Okay. Different kinds of experiments. So, by the way, if you were to do a delay experiment with quantum light, this is what it's going to look like. This is what chaotic light is going to look like. This is what classical light is going to look like. This is another version of our experiment with another time delay. This is what the second order correlation looks like. This is what the classical light looks like. It's just one arm. See, this is second order coincidence. Second order two-fold coincidence, B and B prime without any A. It's close to 1. That's slightly greater than 1. This is classical. So down converting photons do not give you quantum light per se. You have to look at both photons together. If you look at both the photons in entangled field, then it's quantum. But if you just look at one arm of the pair, it's not quantum. Okay. So the experiment about polarization, measurement, about tomography. So this is now in each experiment you do coincidence measurements with A, because then you have two single photons. So it's given that you are looking at the inner arm as well. So you generate some light and then you do generate different kinds of polarization using a half-wave plate and quarter-wave plate. So you can also use these polarization rotation elements to create any state. When you create these states, then you use your analyzer, which is a half-wave plate and quarter-wave plate, as I described earlier in the tomography experiment. And then you have a beam splitter. And then you look at these different combinations. Okay, and do tomography. Okay. And you can find out, you input H state, vertical state, diagonal, anti-diagonal, L, R. These are your predictions and these are your measurements. And there is very close agreement between the measurement and the prediction. With the same scheme that I mentioned earlier in the morning. So you can measure your quantum state, which is really measuring A, B, and phi with high accuracy. You can also do different kinds of neat experiments. So you have this creation and then, but you can create all kinds of nice patterns. I don't want to go into these details. This work was published in one of our articles. And you can compare classical and quantum versions of it. Anyway, how much time do I have for today?
We have some other stuff you can continue. It's okay.
I will just do half of this and write and continue for 10-15 minutes.
Yeah, it's okay.
Okay.
Whichever way, you still have time.
Okay.
Technically, we need to finish at work, but we can continue.
Okay.
It's a nice time.
Okay, so I'll just take actually 15 more minutes. So, so I would like to talk a little bit about interferometry with single photons and erasure. So suppose I have this laser light. There is a classical light or quantum light, doesn't matter. And I have this interferometer, this Mars and interferometer. And now what I've done is that in each of these parts I've put a polarizer. If I don't have a polarizer, on a screen I will see these fringes. Because the interference. If I were to put these polarizers, and these polarizers were crossed, that is, one was horizontal, the other was vertical. Then I put a screen. I will not see any interference, I will just see this classical blob, no interference. Because now I do not have, because when I place these polarizers, I can measure the output polarization, and by measuring the output polarization, I can tell which path the photon has taken. Correct? So I can destroy interference. I can destroy interference by measuring the path. And the path is measured by correlating with the polarization. So this is how most of these experiments done. You measure the path by correlating with the polarization. So this is classical interferometry. It's the high level answer individual path and position and the momentum cannot be discerned simultaneously. Alright. Now what we could do, so we do a series of experiments, classical or quantum, right? Doesn't matter. Results are the same. In which you keep one polarizer fixed and you rotate the other. If both of these polarizers are parallel, it means that the polarizers don't exist at all because then there is no tagging of the path. You can't tag the path because both polarizers are the same. The photon arms remain distinguishable. When the photon arms remain indistinguishable, when the photon arm remains indistinguishable, you see interference. So this is the case when both the polarizers are parallel. When one of the polarizers is rotated, you get this change in visibility. Visibility is the size of the fringes, maximum minus mean. You see the change in the visibility. When the polarizers get crossed, you see complete disappearance of the fringes. The visibility drops to zero. Now, in this case number Hij, in J you have which path information. You have information about the path and that's where the interference fringes have disappeared. The classic photon interference experiment. Now, the good thing is erasure really means that even if these polarizers are crossed, you have which path information, but by placing a third polarizer after the interferometer. So this third polarizer, P3, is now placed after the beam splitter. So the interferometer ends over here. Now, after the interferometer, after the photon or photons have gone through this interferometer, and you have obtained which path information in a way, you can arrange that which path information that was obtained earlier by placing a polarizer at the very end. This is called erasure. You are erasing the which path information by an element added post interferometry, after the interferometry. This is called quantum erasure. So these are the fringes. So A and C represent when you have which path information, and when P3 is at a 45-degree orientation, you recover the fringes, which means at a certain orientation of P3, the which path information that was available previously has now been destroyed. So you are erasing the which path information. This is called quantum erasure. So by changing something in the present, you are unwinding something that happened in the past, in a way. That's why this is such a counterintuitive experiment. And it was more dramatic when you're using single photons. Because when you're using single photons, that one photon, remember photon cannot be split. It's in a superposition of these two arms inside the interferometer. And if you have polarizers in the two arms, then you already know which path the photon has taken. But now that photon comes out of the interferometer and sees another polarizer, and that which path information of a single photon is erased. So the idea becomes more dramatic with single photons. Now we can implement all of this with our single photon quantum source. Okay, so how do we do that? So first of all, this is the Marx-Henry interferometer which I showed earlier. I just want to change this screen a little bit so that. Okay. Now, this is slightly difficult to build in a laboratory. Slightly difficult. So what we do here is instead of these polarizing beam splitters, we use to polarize beam displacing prisms. Now, beam displacing prisms are like polarizing beam splitters. So in a polarizing beam splitter of this kind, however, two orthogonal arms exist at the output. Here we do not have two orthogonal arms with two parallel arms, but slightly displaced with respect to position. So this is also like a polarizing beam splitter, but of a different kind. It's a beam displacement prism. Now, a photon comes in at a certain polarization, and the horizontal and vertical beams are separated. Remember, we have a single photon coming in. So that single photon has two paths, and then those two paths are recombined in the second beam displacement prism. So this circuit, which we implement, or this physical reality that we build on an optical cable is equivalent, exactly equivalent to this. The only thing is that we have a half-wave plate in the middle, because what the half-wave plate does, which is at a certain orientation, 45 degrees, it converts ket H to ket P, ket P to ket H, so that ket H and ket P traverse the same distances in space, so that there is no phase difference between them, which will corrupt the results. So we just want to equalize the paths. So this is our interferometer. It's a version of the Marx-Henry interferometer that is actually built inside the laboratory. Now, so this is our scheme for quantum erasure and quantum interferometry. So this interferometer is placed in one arm of the down-converted pair, the signal arm. The either arm still exists and is used for heralding. Now, you just have one detector here, and you look at the coincidence counts. We already verified that light is one, that light is single photon. Now we have to do interference with these single photons. Now, depending on whether a click is received on A, you find out whether a click is received on B. So these are coincidence counts between A and B. So you're looking at single photons. And then I would like to change the phase between these two paths. How do I do that? I put one of the beam displacing prisms on a rotation stage and tilt that rotation stage along the vertical axis in the horizontal plane. So piezo actuator. And I plot the intensity or the number of coincidence photons received here versus the versus the piezo actuator steps, and I place a polarizer at the end for erasure purposes. And depending upon the polarizer angle, so if my polarizer angle at this post interferometer stage is at 45 degrees, I get the highest visibility. And if my polarizer is at 0 degrees or 90 degrees, I get no visibility. So this is quantum erasure with single photons. Okay. So this is quantum erasure truly with single photons that could be achieved in the laboratory. In fact, one of the kind of allegations or kind of objections to this experiment was that okay, it's not true quantum erasure because this polarizer can be considered to be a part of this interferometer. So Paul Quaid and Anwar and later proposed that one should do another experiment in which you keep the entire interferometer arm fixed and use the other arm and the polarizer and a half-wave plate on the other arm to change the fringes that are observed over here. And that is truly remarkable when you do this with single proton. So we implemented this experiment in the laboratory. So instead of changing the polarizer on this arm, we keep this polarizer fixed at 45 degrees. And then we have a half-wave plate in the other arm. And then we look at the coincidence detections between these two channels. And we do the mathematics. The mathematics is easy to do, and probably you could do this as a homework. I'll share the slides as well. By changing something on this arm, you can change the visibility of the fringes that are seen on the other arm. This is non-locality. So you're doing some manipulation on the photon arm, on the either arm, and something that is far away is changing the outcome over there, without any physical interaction. That physical interaction has happened in the past at the BBO crystalline and entangled photons. So by virtue of entangled, you can do non-local quantum immediator as well. And when we were to perform this experiment, this is the non-local version of the quantum immediator experiment that we have. In this non-local version, look at when beta, which is this half-wave plate angle, when this half-wave plate angle is at 22.5 degrees, which is rotating the inner photon polarization at 45 degrees. You see maximum visibility of fringes on another path. So this is non-local quantum erasure. You're introducing quantum erasure and quantum interference non-locally. So you have a switch here, changing the switch here or changing the orientation of your apparatus here, and something else is changing over here without any physical interaction. Okay, so this truly shows that the photons are entangled there, or the ground converted photons are entangled there in the quantum state and so on. Okay. And if you were to kind of create, instead of an entangled pair of photons here, you would create a separable state of photons. Right? If you were to do that, and you will create a separable state of photons by changing this half-wave plate. So then there is no change in the visibility. So only entanglement ensures that you can non-locally affect one part of the experiment, another part of the experiment by remaining locally at another location in the experiment. Yes. Now, in fact, non-locality has other kind of versions as well. Is non-locality really means this effect that I've shown, that you controlling something at one location, it is affecting something else. Non-locality was predicted in 1935 by Einstein, Prof, and Rosen, but it kind of remained in as a figment of imagination and a lot of debate until 1964, when John Bell came up with his idea of testable, verifiable inequalities that one can quantifiably show whether non-locality exists or not. So to give you a simple example of non-locality, suppose I play a game. And the game is such that we have two boxes, which are called non-local boxes. Each one of them has an input X, this has an input Y, and output A, output B. Two non-local boxes. X, A, B, Y, could be 0 or 1. Now I would like to adjust my outputs such that this condition is satisfied. That is, the product of X and Y equals A exclusive OR with B. Now, there are different ways of playing this game. So, X and Y, if both of them are 0, this must be 0. A exclusive OR with B must be 0. So, if I put A equals 1, B equals 1, the exclusive OR of A and B is 0. So, it equals X into Y. So, this is my configuration that X and A are related because these are input and output on one box. Y and B are related because they are input and output. So, I define this rule. The two parties define the rule. Likewise, if X and Y are 0 and 1, I define this rule. If x and y are 1, 1, I define this rule. But if I follow the 3 rules that I've specified over here, the fourth row, if I implement the same rule on this yellow row, I cannot satisfy this. So I can come up with different permutations of zeros and ones, self-consistent, internally consistent, but I can only make this game to succeed 75% of the times. I cannot do better than that. I cannot come up with a rule book, internally consistent rule book that can break this limit of 75%. Alright? But try to do this on flow, these are non-local forces. Now, okay. However, quantum physics can help you do this. If I produce an entangled state of this kind, and x and y determine my measurement basis. So if x is 0, my measurement basis in one part, in one box is horizontal vertical. If x is 1, then my measurement basis is 45 degrees and diagonal and diagonal. For the second box, if my y is 0, then my measurement basis is 22.5 degrees and 112.5 degrees. If my y is 1, then my measurement bases are oriented in this direction. So if I decide upon this rule and use this as an input state and find out the probability of winning this game with these bases that are changing with an entangled state, then my probability is about 85%. So I break the 75% limit. So this is an example of a Bell's inequality. So if you play this game, if classical reality is true, which means there is no non-locality, nature is local and it's realist, locally realist, then your outcomes must be within that bound of 75%. But if you cross that bound, then nature must be non-local and non-real. So this is an example of Bell's inequalities. So now we can do tests for non-locality and Bell's inequalities with our apparatus and with our setup. For that, first of all, we have to create a nice entangled state in which is phi equals 0. So we need to create a Bell state at H plus ket BB. Physically, when you do this experiment, a small phase factor creeps in, EL phi, because it's never easy to kind of have perfectly matched crystals and the distance between them can never be equal to 0. They are still finite, thick crystals. So you need to adjust this phase, and you can adjust this phase by putting another quartz wave plate or a retarder in the path. And you change this orientation so that the coincidence counts come to a minimum, and in that case you will have phi equals to 0. And you have to prepare a particular input state for the Bell's inequality test. You do that with the help of this quartz wave plate. Now, there are 3 kinds of tests that we perform. There are different versions of Bell's inequalities. The simplest version is Friedman's test. The Friedman's test one defines this parameter delta, which is defined in this fashion, and number of counts when these polarizers at a mutual angle of 22.5 degrees minus the number of counts when these polarizers are at a mutual angle of 67.5 degrees, divided by the total number of counts. If this number is greater than 0, this number is greater than 0, then you have violated local realism. So when you perform this experiment, our number turns out to be 0.095 plus minus the standard deviation, which is greater than 0. You violate local realism. So nature is non-local, it's non-real. You will do this famous test called the CHSH test. So the Bell's inequalities, this can be any standard textbook on quantum mechanics or quantum information will have this test. So if this parameter S is less than 2, where S is defined by this correlation function, then you will have local realism. But our values turn out to be 2.6, 2.6, 2.6, and they differ from 2 by 118 standard deviations, 150 standard deviations, 219 standard deviations. So by this much confidence, we violate local realism. So our photons, single photons, they're really quantum, like in quantum mechanics, is non-local and non-real. The third test that we performed is called the Hardy's test of local realism. This is a slightly complicated test because it requires one to create a certain quantum state. So this quantum state, we first create that special quantum state. It's a partially entangled quantum state, not a totally maximally entangled quantum state. So we create that entangled state. And once we create that entangled state, we find this parameter h. If this h is negative, we have local realism. If this h is positive, we have violated local realism. Our h turns out to be much higher than 0. Look at the standard deviations here, much higher. So we have violated local realism once again. So by a very high confidence, extremely high confidence, unmatched with any other kind of experiment that you do in particle physics or high energy physics or any other physics that I am aware of, we violate local realism. And that's why probably the 2012 Nobel Prize was given to this countering the idea of non-locality in environment. Now, tomography, I have already explained what tomography is, the different quantum states, predicted density matrix. And if you do tomography for 1 qubits, and this is the measured density matrix versus the predicted density matrix. This is a slightly more complicated calculation in which you would like to do 2-qubit quantum state tomography. And doing 2-qubit quantum state tomography is slightly more complicated because you want to ensure that the final density matrix that you get is legitimate. So you need to impose certain additional constraints when you are reconstructing your density matrix. And those constraints come from this auxiliary matrix, which is defined in this fashion, and then you minimize the log likelihood function using what is called the probability estimation technique. Sorry, forget the name. It's a minimization routine that you use, and you minimize this figure of merit and find out your quantums. No, it's maximum likelihood estimation. Sorry, maximum likelihood estimation (MLE). So we use this technique to find out the density matrix which is legitimate. So when we do this 2-qubit quantum state tomography with these photons, remember again how we do quantum state tomography. We have different combinations of quarter wave plates and half wave plates. Inside the two arms, we just change these angles according to this table and measure the outcomes using these polarization beams like this. And from all the data that comes in, so we have all of these different kinds of measurements. From all of this data, we can reconstruct our density matrix using maximum likelihood estimation. So these are some measurement results. Here is one set, here is another set of measurement results. These are just the coincidence detections. And then you can, so for horizontally polarized state, only one term in the density matrix shows up. Vertically polarized, likewise. This is our entangled state in which I showed you the density matrix, which the states, the term, the corners light up, everything else remains the same. So, by the way, this is a complex density matrix. You need to plot the real and imaginary parts separately. So it's possible to do quantum state tomography with single photon. This is the fidelity of the result, how well your measured density matrix matches the prediction. And then we could also do one thing that we do in our laboratory is process tomography. So once you do state tomography, it's also if you have unitary matrix, you want to find out what the unitary matrix is. You just put your operation, your unitary operator, 1 qubit, 2 qubit unitary operator, and pass light of a known quantum state inside this unitary operator. Here we are rotating the state at different temperatures, low temperatures, high temperatures. You can find out what the unitary matrix is and see how refers to different kinds of rotation on the box. Alright, so this is all that I have to present today. I hope I've given you some idea of how practically things look like. tomorrow I'll start with global search algorithm. Then I move to teleportation, one qubit teleportation followed by one bit teleportation, and from that I build my way into cluster state quantum computing with special emphasis on photons. And we'll see tomorrow we can show how the global has been implemented with photons. Otherwise, we'll do it the final way. So I hope it's okay.
Thank you very much.